is a video about secret codes, necklaces, and what's useful, or useless. We're first going to learn about RSA, the crypto system behind almost everything that gets encrypted on the internet, from emails to bank account passwords. It was invented in 1977 by Ronald Rivest, Adi Shamir, and Leonard Adelman, based on a concept thought of by Whitfield Diffie and Martin Hellman. Before we can get into RSA, there is some background knowledge you'll need, so we'll start with a simpler cipher, known as a multiplicative cipher. Say you want to send me an encrypted message. For now, we'll keep the message simple. You need to secretly convey to me the sinister message known as the letter D. Dun dun dun! First, you need to turn your letter into a number. A would become 0, B would become 1, and C is 2, so D is 3. Next, you would use a key, say the number 15, and then multiply your message by your key. You would get 45. Then you would use modular arithmetic to turn this number into a number between 0 and 25. If you don't already know what modular arithmetic is, here's a quick summary. In modular arithmetic, the only numbers that exist are the integers from 0 to 1 less than the modulus, which is some integer that's more than 0. For example, if 26 were the modulus, the only numbers that exist are 0 to 25. If there's a number outside of this range, say 54, you add or subtract the modulus until the number is within the range, so 54 would become 2, since that's what 54 becomes after subtracting 26 twice. 54 is now said to be equivalent to 2 mod 26. It's often seen as the numbers wrapping around to 0 once they reach the modulus, and you can see a visualization of that here. The numbers that line up in this spiral are equivalent to each other, mod 26. Since there are 26 letters, the multiplicative cipher uses a modulus of 26, and 45 minus 26 is 19, so 45 is equivalent to 19 mod 26. You can see how 45 lines up with 19 in the spiral because of this. 19 corresponds to the letter T, so that would be the encrypted message. If this doesn't make sense at first, that's very understandable. This is usually the kind of thing taught over the course of an hour, and I'm trying to cram it into a minute, so feel free to rewatch this part or look it up online. Now that we've encrypted, all that's left to do is decrypt, which we'll do in the next section. You just encrypted your message using a multiplicative cipher. So now you would send me the encrypted message, the letter T, along with the key 15, and I would use the key to decrypt it. Okay, so you encrypted by multiplying by 15, so I can just divide by 15, right? Not so fast. 19/15 can't be turned back into a letter. This is because you subtracted that 26 when the number was still 45, but I have no way of knowing how many 26s you subtracted, because all I saw was the T you sent me in the end. So instead, I have to use something that's called a modular inverse. Two numbers are inverses of each other if their product is 1, so it follows that two numbers are modular inverses of each other, mod n, if their product is equivalent to 1, mod n. This means that 7 and 15 are modular inverses, mod 26, since 7 times 15 is equal to 105, which, mod 26, is equivalent to 1. So you sent me your message, let's call it m times 15. Now to decrypt, I'll multiply it by 15's inverse, 7. So that's m times 15 times 7. We do this because, as we said, 15 times 7 is equivalent to 1 mod 26. So m times 15 times 7 will be equivalent to m times 1, or just m, which is the original, now decrypted, message. So let's apply that. T is 19, times 7 is 133, mod 26 is 3, which corresponds to D, the original message. Congrats, we did it. But there's a small problem. If a spy stole your message, he wouldn't be able to decrypt without the key. That seems good, but that means I wouldn't either unless you send the key to me. And if a spy can steal a message you're sending me, they can probably also steal the key you're sending me, and then decrypt the message. This is where RSA comes in. We'll get to that in a second, but before we can, we need to have a chat about necklaces. Pick a number, any number. I'll use 2. Now pick a different number, but this time it has to be prime. I'm using 3. We're going to make a necklace using these numbers with 3 beads and 2 different colors of beads. Let's try to figure out how many ways this necklace can look when it's unclasped, like it is now. Well, there are 2 colors each bead can be, and 3 beads, so that makes 2 to the 3 ways to make it, or 8. If we were to clasp this necklace, though, 3 different unclasped necklaces would all make rotated versions of the same necklace. For example, purple, pink, purple would be the same as pink, purple, purple, and purple, purple, pink, just starting at a different spot on the necklace. This holds true for all unclasped necklaces, except for the 2 cases where all of the beads are the same color. All this to say, the number of clasped necklaces is equal to the number of unclasped necklaces, minus the 2 cases that are all one color, divided by the 3 ways that the necklace can be rotated, and then adding back the 2 ways that are all one color. This doesn't seem all that impressive, but hang with me for a second. Let's call this number 2 that we picked A, for any, because, well, it can be any number. Then let's call 3 P, for prime. We can generalize our formula to be A to the power of P minus A divided by P plus A is equal to the number of ways that the necklace can be clasped. Now, here's where it gets interesting. The number of clasped necklaces is obviously a whole number, so just this part here is a whole number. That means that this section here is divisible by P, no matter what A and P are. This is called Fermat's little theorem, which he stated in 1640. Before we move on, we're going to rewrite his theorem a little bit. When you say x is divisible by y, you can express that as x is equivalent to 0, mod y. So another way of expressing his theorem is that a to the power of p minus a is equivalent to 0, mod p. Adding a to both sides, you get a to the power of p is equivalent to a mod p. And then dividing by a gets you a to the power of p minus 1 is equivalent to 1 mod p. Yay, we did it! What did we do exactly? Granted, this seems kind of pointless, but that's the reason we did it. It was completely pointless in 1640. Today, though, it's used every day, and you'll find out why in the next section. Fermat's little theorem may have seemed useless then, but today it's being used every day, right under your nose in, you guessed it, RSA. So what's so great about RSA anyways? Here's a way to think about it. Imagine you're trying to send me a locked box. With a multiplicative cipher, you would lock the box and tape the key to the side of the box. Anyone could open that, though. With RSA, there's a key to lock the box and a separate key to unlock it. I tell everyone exactly how to make a key that can be used to lock my box. Then you can lock my box and send it to me, and even if a spy got their hands on it, they wouldn't be able to unlock the box because they need a different key to do that. This means that I can publicize my encryption key and you can send me a message encrypted with it, and only I can decrypt it, because you can't figure out the decryption key just using the encryption key. So how does it work? Let's try to piece it together. We'll start with the knowledge that to encrypt the message, we raise it to the power of E, the encryption key, and to decrypt it, we raise it to the power of D, the decryption key. So after encryption and decryption, the message will be m to the power of ed mod some number n, and we'll work that out later. This might seem kind of random, but it'll become clear why we're doing this in a second. For now, let's start with Fermat's little theorem, which we figured out earlier. Let's first multiply by m, but remember that this part here is still equal to 1. The first insight we can have is that if we multiply the exponent by any number, let's call it h, this 1 will be raised to the power of h. But 1 to the power of anything is just 1, so we can put this h here, and the equation remains otherwise the same. Now, we'll set m to the power of ed equal to m to the power of p minus 1 times h times m. We do this because as long as the equation holds true, m to the power of ed, the message after encrypting and decrypting, will equal m, the original message.
We'll divide both sides by m now, and lastly, these parts must be equal because the bases are the same, so we get ed minus 1 is equal to p minus 1 times h. We can reinterpret this as ed minus 1 is divisible by p minus 1. Like you'll remember from before, that's the same as saying ed minus 1 is equivalent to 0 mod p minus 1. And adding 1 to both sides, we get ed is equivalent to 1 mod p minus 1. That also sounds familiar. That's the definition of modular inverses. That means that we can pick any number e and a prime p, and then calculate d from that, and m to the power of e mod p, the encrypted message, raised to the power of d, will give us m to the power of ed, which we just proved is equal to m, as long as e and d are inverses mod p minus 1. It pretty much works. There's just one problem, which we'll cover in the next section. For someone to encrypt a message using the system we worked out, they'll need to know what E and P are. But with that knowledge, they can figure out D. So if I publicize the encryption key, people can work out my decryption key too. We need to ramp up the complexity of our cipher a bit so that it can't be cracked by someone who knows the encryption key. So let's do the same math one more time, but this time with new variables. Our new prime number will be called Q, and we'll use K instead of H. I'll write out all the steps with the new variables, and there they are. Now, to add complexity, instead of just using one or the other, we're going to combine the mod p minus 1 and mod q minus 1. Now, since we figured out that ed minus 1 is a multiple of both p minus 1 and q minus 1, it has to be a multiple of the LCM of p minus 1 and q minus 1. So, our more complex requirement is that for m to the ed to be equal to m, both mod p and mod q, e and d must be inverses mod the LCM of p minus 1 and q minus 1. So why is it better for m to the power of ed to be equal to m in both mod p and mod q? Well, this means that we can combine the mods, like we did with the other equation, and say m to the power of ed is equal to m mod n, where n is just the LCM of p and q. Since p and q are prime, their LCM is just their product, so n is just pq. Great! Our final RSA system is that to encrypt, you calculate m, your message, to the power of e mod n. And to decrypt, you calculate m to the power of d mod n. But is it secure? Well, to encrypt, you need to raise m to the e mod n, so we'll need to publicize e and n, so people can send us messages. But knowing n, you can only figure out p and q by factoring n. Now, with small numbers, that's easy, but when RSA is used for things like emails and bank account passwords, p and q are primes hundreds of digits long, and it would take modern computers thousands of years to factor n's that large. This is why RSA is an unbreakable code. I hope you learned a lot about RSA and Fermat's little theorem, but mostly I hope you came away with the message I really want to use this video to convey, which is that even when a formula or a fact seems kind of useless, even if it just seems like a fun little game but nothing of substance, it could have massive implications in the future. Thank you for watching.
Created using Powtoon.